Ladies and gentlemen, welcome to our help videos on 8-26, fun with double displacement reactions. Hopefully you read the directions to this assignment, where you're going to need to use the solubility table to predict and balance these reactions. Remember, just putting aqueous solutions together does not mean a double displacement reaction is going to happen. In order for a double displacement reaction to happen, one of three things must occur. You put the aqueous solutions together and a solid precipitate forms. Or you put the aqueous solutions together and a gas forms. Or you form a liquid, which is what occurs in an acid-base neutralization reaction, which is a specific type of double displacement reaction. So you will be needing your solubility table to determine if, when putting the aqueous solutions together, to see if a solid precipitate forms. Here we go, reaction number 1. In this reaction, we're putting magnesium nitrate solution and mixing it with potassium hydroxide solution. So we have one container that has magnesium ions, Mg2+, floating around with nitrate ions, NO3-, and then we pour in potassium ions, K+, and hydroxide ions, OH-. So what happens then is, in this container we now have hydroxide ions bumping into magnesium ions. And when that happens, the magnesium ions and the hydroxide ions will pull together. The magnesiums are 2+, the hydroxides are 1-, and if we look up on our solubility table, we have our magnesium right here. Here's our hydroxide right there. We see that it's insoluble. So when those ions bump into each other, water cannot keep them pulled apart, and it will precipitate out of solution as a solid. Still floating in the solution, however, are the potassium ions and the nitrate ions. K+ and NO3- are still floating around. They will not precipitate out of solution. Here's the potassium ions. We head on over to the nitrate ion column, which is right here, and we will see that they will stay in solution. They are soluble. We now have to balance this reaction. Where do we get the formula MgOH 2 times? Well, magnesium's 2+, the hydroxide ions 1-, we crisscross. Where do we get KNO3? The potassium ions are 1+, the nitrate ions are 1-, crisscross. We now would have to balance this. We have 2 hydroxide ions right here, so we need 2 here. So we put a 2 in front. That gives us 2 Ks, so we need a 2 in front of the K, and that balances out the nitrate ions where we already had 2. The driving force behind this reaction is the formation of a solid precipitate, which can be abbreviated PPT. In our next reaction, we are dropping a piece of zinc sulfide salt into an aqueous solution of hydrochloric acid. What's going to happen in this reaction? Again, we're dropping a piece of solid zinc sulfide into hydrochloric acid. Hydrochloric acid's always going to be 100% ionized in solution. It'll dissociate 100%. It's one of our 6 strongest acids, so we'll have H+ floating around and we'll have Cl- floating around. What happens here is the zinc will bump into the chlorides. That's not a problem. But we'll have the S2- bumping into the H+ floating around. That is a problem, because the H+ will grab onto the S2- and form the H2S molecule, hydrogen sulfide, and this can be a gas at temperatures slightly above room temperature. H2S is a volatile liquid which goes to gas easy. I think it's somewhere around 26 Celsius or something like that, and it will go to a gas. This is another of the driving forces of a double displacement reaction. Formation of the gas, it's the second one. So what drives this double displacement reaction to occur is a gas. Remember, double displacement reactions happen when the first thing here ends up with the second thing here. These two green things end up together and leave behind the zinc chloride floating around in solution. The zinc chloride will stay in solution. How do I know that? There's zinc, there's the chloride. S is soluble here. S is soluble here. S does not stand for forming a solid. On this table, it stands for a soluble. The I's stand for insoluble on that table. In our next reaction, we have aqueous magnesium nitrate. And we have poured together and mixed with aqueous copper 2 sulfate. So we have Mg2 pluses floating around with NO3 minuses, and we pour in Cu2 pluses and have SO4 2 minuses floating around. Yes, the first thing here will bump into the second thing here. So the copper ions will bump into the copper 2 ions will bump into the nitrate ions. When they bump into each other, will they precipitate out of solution? Well, here's the copper 2. We go on over to the nitrates, the NO3s. Nope, they are soluble. They will not precipitate out of solution, which is written right here. They will not precipitate out of solution. It's aqueous. And then we have the Mg's bumping into the SO4s. We have the Mg2 pluses bumping into the SO4 2 minuses. So we look up on the table. There's the Mg. We go straight over to the sulfates, the SO4s. They are S soluble. They will stay in solution. So the magnesium sulfates will not precipitate out. The copper 2 nitrates will not precipitate out. Everything will stay just fine in solution. No problems will happen. There, now we got the aqueous back up on that line. And for that reason, no reaction will happen. Nothing is going to precipitate out of solution. No reactions will happen. Our next one, we have phosphoric acid. And we have calcium hydroxide. And we are told this is an acid-base neutralization reaction. How do I know this is my acid right here? We have the phosphate ion. The phosphate ion is 3 minus. And when we have hydrogens on our negative polyatomic ions, they are considered to be acids. We have calcium hydroxide here. And if you remember, the hydroxide ion is the strongest base we can have in solution. So we have an acid and we have a base. And an acid-base neutralization reaction is a special category of neutralization, or a special category of double displacement. The calciums from here, the first thing here, will react or bump into the second thing here. The first thing here, this light blue one, the calcium, will bump into the phosphates. What happens when the calciums floating around bump into the phosphates that are floating around? We look up onto the table. Here's my calcium, 2 pluses. They're bumping into the phosphates, which are right here. And we see that there's an I there, and that I stands for insoluble. So the calcium phosphates, when they bump into each other, they grab on, and water will not be able to keep them pulled apart. They will precipitate from solution. So one of our driving forces is met right there. The first thing here bumps into the second thing here, the phosphates, and they precipitate out. Then we have the H's right here bumping into the OH's right there. The first thing here joins with the second thing here. And that is written in color this way. Again, this is put in a separate color because it's sometimes hard for students to see that the H's here are breaking off and joining with the second thing there, the OH's. HOH is another way of writing water. Water is a liquid. So this another driving force of double displacement reactions is the formation of a liquid. The liquid is HOH. So we have two conditions being met. We have two driving forces in this reaction, the formation of a liquid along with the formation of a solid precipitant. Now, how do we balance this one? We have three hydrogens joining up in the ratio of two hydroxides, 3 to 2. The smallest number 2 and 3 both go into are 6. So we put a 6 in front there. We have two hydroxides there, so we need a 3 in front. 3 times 2 is 6. We have two hydrogen ions breaking off the phosphate. As it's acting like an acid, acids are substances which kick off H pluses. We need a 2 in front. 2 times 3 is 6. This 3 in front will give us the 3 calciums we need, the 3 calcium ions. This 2 in front will give us the 2 phosphate ions. Why is it Ca3PO4? Because the phosphate ion is 3 minus, the calcium's 2 plus, we crisscross. So this is a double displacement reaction, more specifically an acid-base neutralization reaction. Acids kick off H pluses. Bases, the hydroxide ion here is the base. The bases accept the H plus. So the OH accepted the H plus to form water, HOH. We continue on to the next page. On this next page, we have potassium carbonate, aqueous, reacting with barium chloride, aqueous solution. Remember, the first thing here is going to bump into the second thing here. So the potassium's ions bump into the chloride ions when we pour these two solutions together. What happens when the potassium bumps into the chloride? Here's potassium right here on our list. We go over to the chloride column, and there's an S there. S on this table stands for soluble. So the potassium ions and the chloride ions remain freely floating around. Water is able to keep them pulled apart. Bariums, however, we have barium ions that are going to bump into the carbonate ions. The first thing here bumps into the second thing there. When the barium bumps into the carbonates, here's the barium, here's the carbonates, there's an I on the table, which means it's insoluble. When these two ions bump into each other, they grab on and water cannot pull them back apart. The bariums are 2 plus, the carbonates are 2 minus. We crisscross. The formula is BaCO3. It will precipitate out a solution. Potassium's 1 plus, the chlorides are 1 minus. Crisscross. The formula is KCl. We have 2 Ks here, 2 KK pluses here. We have 2 Cl minuses here, so we need to put a 2 in front in order for those to be balanced. We're going to stop the video right here, and we'll pick up on our second help video. We'll pick up with number 6 on our second help video, and we will continue on at that point. So if you need help on the remaining ones, 6 through 10, watch the next video. Hopefully this help video is providing a little less or clearing up any confusion you might have. Thank you.